pull up some charts here, guys, but bear with me for a moment. Okay, so this is actually a whole lot more detailed one than I wanted, but you remember last week when somebody asked what ISO was, and I was like, oh, we'll go over that later. Well, now is later. It's something we need to go over now. So when we're looking at ISA deviations, and I know we've kind of briefly touched on ISA. So what ISA is they basically have assigned a temperature to sea level, and then and that temperature is 15 degrees Celsius. And that's just what we use standard across the board. That is called ISA. And actually, I'm struggling to remember what ISA stands for now. It's like International Standard Atmosphere. So basically what it is that at sea level we're 15 degrees Celsius, and then each 1,000 feet we go up, it goes down in temperature by 2 degrees. And so at 1,000 feet, what is ISA for us?
13 degrees.
13 degrees. So at 20,000 feet, what would ISA be? So if we take 20,000, so we're going to take 20 times 2, so it's 40 degrees, minus 15, which is our ISA. Let me pull up an altitude chart here.
I got for 20,000 feet, standard should be negative 25 degrees Celsius.
Yeah, that's correct.
Cool.
Let me see if I can find a good representation, though. Sorry, guys.
Hey, Davis,
Yeah.
does the ISA, is that kind of just a universal, doesn't really matter if you're near the equator or the pole, or is that complication that we'll deal with later?
It's just a universal thing, and a lot of it is just kind of how we create a deviation for a lot of these charts and stuff.
Okay.
Wikipedia's got to have something. Wow, striking out. Okay, so let's just say I'm going to use my little pen. We are down here, and this is sea level. There's a little red tree. Here's our little plane. And then this is our runway. So down here, we're looking at 15. So let's say up here, we'll just go with 10,000 feet so I don't clutter this screen. Okay, so this big one's 5,000. So up here, we're at 10,000 feet. So what we would do is we've got 10 times 2 is 20. So then to find from there, we're going to do that. Well, that's actually, it's going to be negative. So, because it's going up. So we go down in temperature by 2 degrees for each 1,000 feet. So -2, -4, 6, 8, 10, 12, 14, 16. I missed a line somewhere. Did I? No? Okay. So -20. And then we're going to find what the difference is between that and 15. So our standard temperature, our ISA at 10,000 feet is going to be 5 degrees, negative 5 degrees.
Would you subtract the 20 from 15, or do you do 15 from 20?
15
I
from,
thought it was the opposite way.
well, it's going to be the opposite. So this is going to be negative. So you're going to be taking 2 degrees away from this. So if we do a minus 2 here, we're looking at 13. And then minus 2 here, we're looking at 11.
All right, I see it now.
Yeah, so we're going to slowly go down here. So 11. This is going to be 9, 7, 5, 3, 1. And here we're going to hit negative 1. And then negative 3. So what you can either do is just know that it's 20 minus 15 and that it's going to be negative. Or you can do negative 15 or negative 20 because you know it's going to be a negative degree up here. And then plus 15. So if it were actually up here at 10,000 feet, we'll just put K for 10K. If it were actually, let's just say negative 10 degrees up there. Our ISA deviation is how far away negative 10 degrees is from negative 5 degrees. So when we're looking at these two numbers to figure out our ISA deviation, what we're trying to do here is figure out what we need to add or subtract to this to get this. So then we're looking at, we're going to end up subtracting 5 from this. So we can either take what it actually is and we can just subtract the 5. Well, we just take the difference. And then we got to look and see, okay, so negative 5 plus 5 would be 0, but negative 5 minus 5 would be negative 10. So our ISA deviation is ISA minus 5. Does everyone get that?
Yeah, it makes sense.
Yep.
Okay. So the reason this is important for us is because our engines are actually only, so like on takeoff, our engines are only rated to ISA plus 15. That's the hottest we can take off at. So that doesn't really give us like a specific number. So there's never like a, oh, it's too hot, we can't take off. And the reason why that is there's not enough air going through the engine. Let me see if I can find that beautiful picture of the engine we found last week. Huzzah! All right. So what we're looking for when we have this engine is all these air particles I mean, this is a fair amount of dots. I'm not doing this every time. But we want these air particles, these red dots, we want these going through the engine or around it on the bypass air, either one. But that's how we create force, is pushing air back out of this. So if we can't get air into this, we can't get air out the back. So at high altitudes and at high ISA deviations, we don't have as much air going in there. High altitudes, clearly the air is thinner. Although our planes work great at high altitudes while we're in cruise, trying to take off with all the extra weight can cause us a lot of problems. And but the hot air is kind of a different one. So let's say that this is ISA. So there's a fair amount of air molecules here, and those are going through our engine. Those are helping our performance. Those are helping our takeoff, and we're getting a lot of power from those. So if it's cold, does anyone know what happens to the air?
Does it get more dense?
Yeah, it gets more dense. So I'm only going to do it on the top this time. So when it's cold, there's less energy in the air, and these air molecules are not vibrating as much, they're not moving around as much, and they get more dense. So we actually get great performance numbers when it's cold outside. It's very rare that we end up takeoff weight restricted for our normal routes. When it's hot, though, we end up takeoff weight restricted a fair amount, especially coming out of Denver, because it's both hot and high. So we're already high up in elevation, so the air's a lot thinner. There's not as many molecules up there. But when it's cold, we have much more dense air molecules and they can go through this engine, and we can get a lot of performance out of these. We can push a whole lot more air out of the back of the engine. When it's hot, though, we don't have near as much air, because all these air particles are just moving around. They're just bouncing around like crazy, but they're very energized. And so the air is a whole lot thinner, even though when we walk outside and you try and go for a run or something, it feels like the air is just heavy and thick. And especially if you guys have ever been in a place where it's humid, you just feel like you're swimming through jello. But so if we don't get much air into the engine, we can't get much air to explode in here, and we can't get much air to push back out of the back to give us a lot of thrust. So when we end up with ISA deviations like ISA plus 15, I mean, at sea level, that's 30 degrees. That's pretty hot.
Hey, Davis?
Yeah.
With automobile engines, it doesn't happen often, but sometimes higher humidity does lower performance.
Uh-huh.
Does that happen with jet engines? Like, all things being equal between, say, Arizona and Hawaii, would you get less performance in Hawaii because of the humidity, or does that not really affect jet performance?
It does. They don't like the humidity as much.
Okay.
Yeah, I mean, in that case, think of it almost as like a person. Like, would you want to go outside and go for a run if it was, really hot, humid, and you're on a mountain in Denver? That's like the perfect storm. Like, absolutely not. I don't want to do that. Do not sign me up for that 5K. That sounds very miserable. But
so follow-up is, does humidity is that something that we ever have to account for, or is it the effect small enough that it is what it is, but we're not going to deal with it?
We don't really deal with it as dispatchers, honestly. It's all pretty well computerized. But then, yeah, like back to the human part, like if you were, like if it was kind of chilly outside, it's a whole lot easier for us to take off running. So just kind of think of it like that. And yeah, they don't like hot. They don't like high. They're not real big on humidity. What we want is we want a lot of air going through here and pushing out the back to create force for us, to create thrust. So when we have these isodeviations, and this will all kind of make sense later when we look at some charts. Yeah, so when we're looking at, different things and it's just super hot outside, that's why these engines aren't rated for those, is because they're not rated for somewhere where there's not a lot of air going through the engine. We actually did just get, though, at SkyWest, we got permission, and Americans started working with Canadair, Bombardier, to get us ISA plus 20 on some of our 700s. But just kind of forget about that as of this class. Still in the pen. So you'll learn how to read these charts a little later on when we go through weather and stuff. But right now, we'll just kind of look at Phoenix, because I want to go over some weather stuff. So we're going to look at different isodeviations. Okay. So let's just start at 6,000 feet. So at 6,000 feet, what would ISA be? So let's think about this. I'll go through a couple of these with you. So 6,000 times 2 is 12. So ISA is 15 at sea level. Oh gosh, what did I?
-12.
Yeah, sorry, -12. I just went totally blank. Sorry, guys, I brain farted. So we're looking at 15 minus 12, because we're trying to find our what ISA is. Okay, because we go down 2 degrees with every 1,000 feet. So if we're going all the way up to 6,000 feet, we're going to go down 12 degrees. So ISA is 3 degrees. Sorry, I didn't mean to do that negative there. Whoops. There's no just erase one thing. Alright, just know that it's 12. Or, sorry, 3. There we go.
I was going to say, just turn that negative into a positive and call it good.
Ah, that would have worked too. So we're 3 degrees. So what is the ISA deviation for us here?
So at 6,000, we're at 24 degrees Celsius.
That's hot. So what we're going to do is we're trying to find the difference between 24 and 3.
Okay, that'd be 21.
So,
Is that a positive 21?
well, what do we do? What are we going to do to this 3 to get 24?
It's -3. Subtract 3 from 24.
Yeah, so subtract 3 from 24. Since this is a positive 3. So 3 plus 21 is going to be the 24 degrees. So we're going to be at ISA plus 3, or plus 21, sorry. Just super hot.
And that's outside our limits. We couldn't take off at 6,000 feet.
We'd have to look and see what the airport elevation is. It's probably actually fine to take off in Phoenix. We take off in Phoenix all the time when it's super hot. There's a lot of factors that go into that.
All right, I'll take your word for it this time.
Yeah, that's a can of worms. Okay, so why don't you guys do 24,000 and tell me what that is? Tell me what ISO would be, and then what our deviation would be.
The ISO's 33 degrees. And
So
then
negative
that,
33, right?
oh yeah, negative 33.
So we'll just do 24 times 2, 48, minus 15. Yeah, so it's going to be negative 33 up there. It's going to be cold. So then what is our actual temperature here is going to be negative 18. Just this part of number here. So then what's our deviation?
$15 degrees.
15 degrees. So what are we at? ISA plus or minus 15?
Plus 15.
Plus 15, yeah. So we could just find the difference here of 18, 15 degrees, and then we'd be adding 15 to that negative 33 to get up to a nice balmy negative 18.
So is that 15 limit, whatever, I can't remember how you said it earlier. Is that only for takeoff?
Pretty much.
Okay. I'd imagine once you're flying, you're just kind of flying, but
Yeah, I mean, it's cold up there, so you're still like pretty good. It's still getting a fair amount of air through there.
cool.
And there are some times where it limits us. It just doesn't like the computing. We do get weight restricted coming out of Phoenix. During the afternoon, I guess it happens. Wouldn't say often, but from time to time. Okay, let's do another one here. Let's go to somewhere that's not so hot. Let's see how Seattle is today.
Hey, Davis, did you say what those first 4 digits are?
No, it's wind, but this
Okay.
this chart is actually a whole can of worms. I'm just kind of looking to see what our differences here are. So actually, if
Those are just for a later date, right?
yeah, those are for a later date. We'll go into those later. But it's basically just like where your wind is coming from and the knots. But
My computer's been glitchy, so I wasn't sure if I just missed something.
no, don't worry about that. Those are fine. Just we're worried about these last 2 digits here. And then once it actually goes up to 30,000, it's always negative. So you don't have to worry about putting the negative side in. So we're still just worried about these last 2 numbers. This is basically just like a wind and temp. Yeah, wind and temps data up here. But that's pretty much all it is. So why don't you tell me what ISA is at 12,000 feet?
-9, and it's 0 now, so the deviation's 9,
Yeah.
right?
So, yep. So we'll have 12 times 2, 24 degrees minus 15, so we get 9 degrees. Or negative 9 degrees, sorry. And then, so it's 0 degrees right now, so we're going to be ISA plus 9. Everything's pretty much ISA plus something right now because it's summer and it's hot. So let's do 30,000. So we've got this here as negative 39 degrees. Let's see what ISA is and then what our ISA deviation is.
-45 at the deviation of 6.
Yep. So, but what is it? ISA, is it plus or minus 6?
Gonna be +6.
Yep. So negative 45 is going to be colder than 39, so ISA plus 6. Are there any that are ISA minus right now? Spokane is close. Guess not.
So your deviation, that's the difference from actual temperature to your ISA difference, right?
Yeah. From
Okay.
what
And
ISA
it's
is to
the actual
what,
temperature.
yeah.
Okay. Thank you.
Yep. Okay. So we'll kind of go into some performance charts today, which is why I prefaced with the ISA. One of the biggest things to remember when we're flight planning is that we're always planning as though an engine could fail somewhere. So what this first kind of goes into is how to select altitude for short distances. So just kind of talking about our takeoff weight here. And then distance. Some of these seem realistic. Some of them, if it's hot out, they may not be getting to. So like if we're taking off at 54,000, we're heading 50 miles, get up to 12,000. If we're heavier, big takeaway from this, I guess if we're heavier, clearly we're not going to be able to get up as high. You can see it goes down in each row. Sometimes by a lot, 37 to 31. This is actually, so if we were doing Mach 7.4, this kind of shows us if our gross weight and flight level, kind of what would be limited to. So if we're 70,000 pounds, we could go up here, and at ISA plus 20, we're limited to probably about 370, maybe just above. So clearly, with this ISA, I mean, this is just kind of showing if it's hot out, we're not going to be able to get up as high because there's not as much air up there. Plus, if it's hot, we're not going to be able to climb as well. This is basically the same thing, but just in Mach 77. This is just for planning long range cruise and fixed Mach. Alright, next we'll kind of go into some spaghetti charts here. So these are totally readable, I promise, but they're not that readable. Let me show you with the example they've got up here. So basically this is just going to kind of show us a rough layout of like what our trip fuel and trip time should be. So for trip distance, we're going to be in 380 nautical miles. We're going to have a 40 knot headwind, a cruise altitude 29,000, and a landing weight of 57,000. So determine trip fuel and time. Enter with trip ground distance correct for anticipated wind condition, and proceed vertically to the cruise pressure altitude. Trip fuel is read to the right for the lower set of the altitude lines, going to the reference landing weight and correcting to the actual landing weight using the guidelines. Trip time is read to the left from the upper altitude lines for isotemperature. So first we'll try and get this trip fuel and we'll see if we get it right. These don't always happen perfectly. Alright, so on these, we start at the bottom here. And basically what we're going to do here is we're going to look at our trip distance. So we'd say 380 nautical miles.
Yeah.
So 5, 6, 7, 8. So we'll do 380 here. And then we'll actually just go straight up to our line of reference. So we go up to our line of reference. And then we use these curved lines to kind of let us know where we're going to go next. So a headwind is going to be taking away from us. So a headwind is going to be negative.
We had a 40 knot headwind.
So if we have a 40 knot headwind, we're going to be looking right under this line here. So we basically follow this up. I wonder if I can draw these any good. We're going to follow that curved line until around, that's probably around 40. And then we follow that up. And what altitude are we looking for here?
29,000.
So 29,000 right there. So we would take this.
Are those flight levels right there? We can't read that.
Oh, yeah, those are flight levels. This is
Okay.
reads 290. I can't hardly read it either. There's not much way for me to.
That's all good. Just clarifying that it is a flight level.
Let me see if I can. I mean, oh, well, yeah, even if I zoom in, yeah, you can see it. Okay, so we went 380. Get my pen back out. So 380 to there. 40 knot, probably around there. We're going to take that up. Whoops. Move that all around. Okay, just ignore those dots now. Okay, so 380 up here. Over to here. Okay. Somewhere pretty close to this. So we get on that 290 line. Wait. So as soon as we hit the 290 line, then we start going over here. And then we follow these curved lines up with it until we hit, okay, so we hit around there. So we went up, we hit the 290 line, we go over. Now we're looking at, what was our landing weight?
I wrote down 57,000 pounds.
57, all right. So we're probably going to be right around in here. So we'll take this on up. So we'll curve this up to follow these lines until we hit about 57,000. And right there, because we're cooking down to here. So we want this to match up with our landing weight. So then if we just go straight across from there to about here, does everyone agree that's, whoops, oh, I screwed that one up, but right about there. That's where it looks like it matches up. And that's between 4,000 and 4.4. I'd probably, I don't know. My unofficial estimates will call that 4.2. It's probably a little less than 4.2, but I probably also screwed up a few places around in here. What was it supposed to be? I think it was supposed to be that, wasn't it?
The trip fuel was the one I didn't have the opportunity to write down.
Oh, sorry. 42.
Nice.
So I did it right.
Almost like we know what we're doing.
Almost. Okay, so now we'll see if we can find the trip time with all these. Oh. Okay, so we were at 3.8. We went up to over here. Stay around on this side of the line. We hit our lines around here. We go over. Maybe 60, I don't know, 65, 70 minutes. It's not positive I did that one right, but close. 70 minutes. So that one we just go all the way up, and then we hit the lines about where it's at, and then we go on over. Yeah. These are almost always like never on. Like it's really hard to actually get the answer totally correct on these. So let's say, and you guys also have this in your, do you guys have access to the lesson plan page?
Yes.
Oh, okay. So yeah, it's in there. Or if you go to the flight planning page and open that first one, the CRJ flight planning, these spaghetti charts are in here too. So I'm going to have y'all do one. We'll pull up our handy dandy things here. So what is this? So we're doing Mach 77 in this. Change that to 77. Where are we flying from? Where are we flying to? Anywhere in the contiguous United States.
Austin, Texas.
Saginaw.
Saginaw to Austin, Texas.
MBS.
That is a random city pair. That's like an Allegiant flight city pair. All
We
right.
fly there. I had to memorize it.
Yeah. All right, so our distance is going to be 1,030. Do we even have that on here? We have it on the next one. We have it on the next one. We've got it on this one. This one's even more complex, though.
Let's find a shorter route then.
Yeah, let's
Stick with
find
the
a
one.
shorter route and do with something that's a little less complex. Saginaw to Detroit. And then we'll do one to Austin later. We're just going to pretend that we're doing real short distance here. So 85 miles. Dang it. We'll go Saginaw to Bloomington. So Bloomington, Illinois used to be like my favorite airport. I went to the University of Illinois, which is like right over here. And so I used to fly in and out of Bloomington all the time. I had flight benefits then as well. And there was one time where I was running late to the airport and checked in, or no. This was back in the day when you couldn't even check in on your phone. And so I had no way of checking in, and I was going to show up like 30 minutes before the flight was supposed to depart. So they were supposed to basically be like boarding as I got there. Also, they have free parking there, which is also pretty awesome. So I booked it in, parked, ran inside, and I had flown in and out of there so much that the gate agents knew who I was. And it's one of those small airports where the gate agents are also like the ticket counter agents and the bag personnel, and they do it all. And the airport, I think she was like the head Delta operations person there, and she was awesome. And when I ran in the door, she goes, "I had a feeling you were going to show up," and just slides my ticket across the counter. And she's like, "Did you have a bag to check?" I was like, "Oh," I was like, "Yeah." I was like, "Actually, I did." She goes, "All right." Well, she's like, "I went ahead and said that you checked one anyway." She's like, "Here's your stuff." She's like, "I already checked you in and everything." And I threw my bag up there. She slips the check bag thing around it and grabs it. And she's like, "See you on the other side." And then just she grabs my bag and like runs back behind the counter and through there. She had checked me in, and it was awesome. She saved the day for me being late. So that was my favorite airport for a while for that reason.
Pays to be a regular.
Yeah, I was a regular. All right, so 285 miles is what we're going to say.
You still need a headwind, an altitude, and weight.
Okay. Our headwind, let's see, we can actually go here and we can find our headwind. So South Bend is right in the middle of those. Where is it? Am I blind? Does anyone else see it?
What's the abbreviation for it?
SBN. I would think it would be in here. We can use Indy. Indy's close enough. So we're going to fly at, well, why don't we use our other chart? Our short distance chart. So what did I say our distance was? 285?
203, 25.
We'll just say we're going at, we're probably not going to get up that high, realistically. Let's say we're going to go at flight level 300. So 20 knots. Our headwind's going to be about like, it's actually not much. Just say it's 20 knots. It's going to be around that. So we got a 20 knot headwind. The jet stream is pretty high during the summer. The jet stream actually lowers in altitude during the winter and also moves further south. So during the summer, we really don't have too bad of headwinds or too good of tailwinds. So 20 knots at flight level 300. And what's the last thing we need?
Some weights.
Weights. We're going to be landing, let's say Bloomington needed an alternate, and so we're going to be landing at like 64,000 pounds. Okay, so 285 miles, 20 knot headwind. Flight level 300. and we're landing at 64. So let's see what our fuel is and then our trip time. And once you get it, don't say anything. We'll kind of let everyone finish. Is anybody still working? All right. What did everyone get for the trip fuel?
I hope this is right, but I got 3,300 pounds.
I got about 34. So those are, I mean, that's basically the same.
That's pretty close.
Yeah. Did anybody get any like big outliers? I mean, I'd say anything between like 3,000 to like 3,500 would be totally fine on this. Did anyone get any like big outliers or? Okay. I'll still kind of go over this one anyway, just quickly. So we're down here, 285, so we're going to be close. We start at the reference line. We have a headwind, so headwind is taking away from us, so that's why it's negative. So 20. So we follow this up to, I mean, I don't know, just under half, which actually easily very easily just kind of puts us on this line. So I just went ahead and followed up the line till we get to this 290 line. It's going to be a little bit above that. We follow that bad boy straight over. Somewhere around there. So when we come over here, we're looking at a 1, 2, 3, 6,400 pound landing weight. So we take this straight over here, and then we follow these lines up. It's going to be somewhere around here, and as soon as we hit this 6,400 pound, we go straight on over. So yeah, anywhere between like this 32 and 36 or so. I'd prefer it be right there in the middle there, but does everyone get that? Take that as a yes. What about time? What did everyone get for time? Did anybody get time?
I got 50 minutes, about.
Yeah, I got around 50 minutes too. Did anybody get anything way different? We basically just keep following this up till we hit these lines. These lines are super close, so on this one it's not going to make too much of a difference, and then we just go on over. It's going to end up right around there. Yeah, 50, maybe a little over. So, all right, let's do one more, and then right around 5 o'clock. Oh, no, my computer's in y'all's time. Right around 7 o'clock, we'll take a quick break. So now, let's, still in the marker. We can go down to I don't want to do this one. This one just looks darker for some reason, just more of a pain. Let's stay under 1,000 miles. So we're going to go to Austin. Let's see how far that is from Salt Lake. Oh, no, to Chaos. Wait, is the majority of people in St. George?
Yes, I think so.
We're going to do a direct.
I think I'm
St. George.
the only one from Salt Lake.
Don't worry, I'm not right now. Normally am, but actually on Mondays when I talk to y'all, most of the time I'm in Georgia. Georgia.
SGU to LAX.
Well, actually, this one works perfect. It's 890 miles. I want to go to Austin. They've got great food.
Let's do it.
This is this place in Austin has this brunch. It's all you can eat. It's one of the most dynamite places I've ever eaten. They have a caviar deviled egg at the brunch. Plus they have like tons of other good stuff. It's like smoked salmon and then of course they have like tons of just this like incredible barbecue. Anyway, sorry. If you ever go to Austin, go to Lambert's for the brunch. But I digress. Got a little excited there.
Also worth the drive to get out to Salt Licks.
Oh yeah, Salt Lick. Man. Whew. That is good. That all you can eat there though. I went there one time in college, and so I was a track and field athlete in college, and I was a thrower. So I was a pretty big dude. I was like 280 pounds at the time. I went to this track meet, and my roommate was too, and we went out there. We convinced our coach to drive us out there, and he and I got the all you can eat while we were there, and we walked away. Both of us just had the meat sweats. It was the most gluttonous display I've ever put on, probably. But it was delicious. I totally agree with your Salt Lake decision. So 890.
Airport.
What?
They put a Salt Lick in the airport too.
Oh, did they really?
Yeah. No all you can eat though.
Yeah. I don't know if I'd be up for the all you can eat anymore. Okay, so we're going 890 miles. Let's see, what's Albuquerque? Let's see what our wind over Albuquerque is. Because we're going to be going like northwest to southeast, so we're going to be trucking along at like maybe 100 degrees or so, give or take. Albuquerque, we're going to go up to 3.5. I can't even. I mean, we'll go with like probably about a 20 knot tailwind. Maybe 20. We'll go with 25. We'll go with 25 just to change it. So 25 knot tailwind. Flight level. Well, you guys pick. What do you think? Flight level. What are we gonna need though? Because we're traveling east from the west. What do we need for flight level?
East is lee, so it has to be an odd flight level.
Boom. Correct. So we'll go. I don't know, 350. What do you think?
Sounds good.
All right. 350, and we're gonna go with a full boat because we're taking a ton of people to the Salt Lick. It's gonna be one adult and 69 children for whoever keeps giving us all the children in our takeoff data. That's who's going to be taking them. You're going to be the chaperone.
Can't believe I've done this to myself.
Yeah, you did this to yourself. So it's going to be you taking 69 children out to the Salt Lick. Actually, but they're like heavy children, so they'll count as people weights. We're going to have a heavy plane when we land. We're going to need an alternate too. So we're going to do a 66 as our landing weight, which would be actually almost absurd. We won't be able to take off with that, but we're going to do it anyway. Okay, so St. George to Austin, 890 miles, 25 knot tailwind, flight level 350, and 66,000 landing weight. Phew. All right, I'll let you guys take this one away.
What was the distance again?
890 miles. All right, is anybody still working? All righty, what did everybody get for fuel?
About 7,300.
Yeah, that's right around what I got too. Did anybody got anything way different?
I got 8,000. A
Um,
little higher than what you guys got. Where did I go wrong?
let's see. Okay, so we're starting at 890 here. So, oh, right there. Okay, so then for our wind, this is the first time we haven't had a headwind. So a tailwind is actually helping us. So we go back down to about 25. It's probably going to be like right there or so. So that may have been where maybe you went. Did you go up?
No, I forgot to account for the tailwind.
Okay. So yeah, then we go up from here. I think like this one's like this one looks like 350. That's the one I went off of. It's almost like right on that line actually. So then we can follow this line over. And then we just kind of follow this curved line up to that's 65. And it's probably about 66,000 there. So then, yeah, 73, anywhere, 7,000 to 7,500 probably be fine. 69,000 to 7,500, or 6,900 to 7,500.
What's the difference between the dotted lines and the solid line?
It's like a corrected line. Just focus on the solid lines, though.
Okay.
It's not. It's just kind of one of those things. I don't. And then what everyone get for time?
About 2 hours and 10 minutes.
So yeah, but yeah, it's actually almost exactly what I got. This right around 130 minutes there. Did anybody else get anything different, weird? All right. Does anybody have any questions on these?
They were daunting at first, but going through them, it's pretty easy actually.
Yeah, they're pretty easy. I mean, it's whenever you get stumped, I feel like I always just like put a little dot, and then then I can like, okay, so where am I at? What am I doing? There's going to be some sort of reference on each side, and then you've got these curved lines that to kind of follow off of, and those all have something on them too. You can typically kind of figure out what you're doing, and so with these, but all right. Let's see. This is probably a good stopping point. Yeah, it's a good stopping point. Let's come back at 7:30.
See you then.
Alrighty.
Hit record, please. Thank you.
Thank you. I appreciate that. I always forget that. Okay, so method 1 is we're flying along and we have an engine fail, and let's just say, let me see if I can just find some mountains.
What were the clearances for them?
Okay, I'll go back into it. Hold on one second. So let's just say you have your plane. A beautiful plane. Okay. So let's just say that you're in this plane and you have planned a method 1. So that means you're able to get all the way up to cruise, and you're at cruise, and then you have engine failure. At any point along that route, we'll just say our engine failure is here, but at any point along that route, you can drift down with one engine and clear all terrain by 1,000 feet, 5 miles on either side, all the way to your destination. We'll just say that's your destination. So 1,000 feet, 5 miles on either side, all the way to your destination. So that means even if you were back here, you just got to cruise, you leveled off, man, things are going great. Boom, blow an engine, you can still drift down to your destination, clearing everything by at least 1,000 feet, 5 miles on either side of the plane.
So, is there a range limitation on method 1?
No, just means you can get there.
I think the range would be just your glide ratio.
Yeah.
Oh no, you still got an engine, so you'd be less efficient, but you could make it, right?
Yeah, you can make it. And actually, if you like we're not going to do ETOPS. We don't really talk too much about ETOPS in this class, but when you talk about ETOPS, one of the big things for fuel planning is if you have an engine failure, like way out over sea, and sometimes you have to decrease altitude because you've only got like one engine pressurizing the plane, so you got to drift down or actually descend down and then fly from there to the nearest airport. And so you've actually got to be able to use one engine to make it all the way back. And they do all their fuel planning based around that. What if we had an engine fail at the worst possible time and we had to go down in altitude and crank up one of the engines and make it all the way back. So some of them can actually just fly with one engine. I mean, if you get on like one of the new like Neos, like the A321 Neos, or like the 737 Maxes, I mean, you could probably like take off and make it all the way to your cruise and land with only one engine. But with ours, we would drift down and have to make it to an airport. So we can drift down at any time and still make it all the way to the destination. So if we cannot abide by that, we then try and go to a method 2. Method 2 means that at some point, I might just hit like a blank screen. Okay, here we go. So we've got our beautiful CRJ 700.
The beautiful CRJ.
The beautiful.
Got all the windows.
Yep. Okay. We got all the windows. Now it looks perfect. So we have taken off. We are in cruise. And then we have a descent and land. Exactly to scale there. Just kidding, it's not. And let's say we have this huge mountain. Maybe I should make this a different color. The mountain is blue now. And now we're going to choose back, and engine failure is going to be yellow now. So we have engine failure up here. So now we've only got one engine. So now we're going to start drifting down. Well, what happens when we can't clear this by 1,000 feet? We'd have to turn around. We can't just fly into it. So we can't do that. We'd be drifting down. We'd crash into the mountain. There's no survivors. No one gets salt lick. It's a horrible situation. The barbecue goes to waste. So then what we have to do is we will turn back around and head to an alternate. As long as we can make it to the alternate, to a drift down alternate, by 1,000 feet of clearance, or actually 2,000 feet of clearance, 5 miles on either side, then we're good. So what happens here is there's going to be a point where we are not allowed to it's a point, and if we have engine failure on this side of the point, we go to a specified alternate. If we have engine failure on this side of the point, then we go to another specified alternate, because from here we can probably still make it down with 2,000 feet of clearance into our runway. Everyone gets barbecue. From here, we will probably not clear that. So from here, what we'd have to do is turn back around and go to our alternate. In this case, it's also our departure airport. You guys get that?
Yeah, that makes sense.
Oops. I think my picture was better. I'll draw another one in a minute.
Does that point have a name of like when the decision has to be to go to 1 or 2?
It has a name, but it's actually different. So for like overwater like ETOPS has a different name than like SkyWest has. I actually don't even know what the name SkyWest calls it, because it's not like really on the release. It just kind of shows us the point. But Trying to think of what it is now. Oh, it actually is the point of no return. Critical point. That's what it is. The critical point.
Thank you.
Yep. So let's go to... I went and found a flight earlier. So Fresno to Denver. If we look on here, I use Firefox because my computer's so old it doesn't support Chrome anymore. And it really annoys me because I'm so used to everything else. Whoops, too far. Maybe this will show it better. Okay. So, Fresno to Denver, we all know there are huge mountains up here around Salt Lake. We can see this range. We can see these over here. There's also a large mountain range in California. And it goes right here. So we have Fresno right here. Denver over here. So let's say we had engine failure right there. Do you think by, because we get to cruise pretty quick, do you think that by the time that we have engine failure here, we'll be able to drift all the way down to our alternative Denver, even with all these mountains right here?
No.
And getting over this, I mean, it's a massive mountain range right here. No, so we actually use a method too on Fresno to Denver, and half the time it actually shows up as we have Fresno, and then it gives us a point about right here. I'm going to go back to Fresno if we have engine failure, and then once we get over this, or past that point, it takes us to Reno. But then once we get another point along that route, it says, okay, we're good enough. I can't ever remember where it is. It's like somewhere over here or some. And it says, okay, now we can drift down to Denver and we're good. Today, unfortunately, it didn't. It just gave us Fresno and Denver, but I'll still show you anyway. So we have Fresno to Denver. It's actually in a 200. Check that out. 48 knot gusting winds, Denver. That's pretty incredible. Okay, so this is where we get to our drift down phase on our release. That's kind of what I wanted to show you. So this is what it looks like for us at SkyWest. So we have a from, a to, and our drift down alternate. So from Fresno to 20 miles northeast of Fresno, if we have engine failure, we turn back around and go to Fresno. So from Fresno, and our route kind of goes up this way. So to 20 miles northeast, so until we get to about here, we have engine failure, we go back to Fresno. We don't try and make it over these mountains and then over these mountains and over these mountains. If we have engine failure, we just go back to Fresno. This is how we plan it, that is. In real life, they're probably just going to land at the nearest airport. So we have this point, 20 miles northeast of Fresno, we go back to Fresno. That's our drift down alternate. It just so happens that it's also our takeoff. After that point, we have actually calculated that we can drift down with engine failure, clearing by how much? If we're in a method 2, how much are we clearing by?
1,000 feet.
2,000 feet. So 2,000 feet, 5 miles on either side, all the way to Denver. Which is kind of baffling. And so, 20 miles northeast of Fresno, all the way to Denver, we drift down to Denver. Now, in reality, do you think if they're flying right here and they have engine failure, do you think they're going to make it all the way to Denver? Do you think they're going to just, we're going to go for it. Let's make it to Denver.
Not a chance. Not even a chance.
Not a chance. They may not even chance it to go all the way to Salt Lake. They may probably just put it down right here in Provo. Yeah. You will probably never find a pilot that would actually do that. Because then, you're flying with one engine. What if you have the other engine fail? So, but that's just how we calculate it. And it has to be calculated by that with, it's automatically calculated in our fuel burn and it takes into consideration all the mountains and all the buildings and everything along our route. So these are big. Method 1, what's our clearance?
1,000 feet and 500, 5 miles lateral or horizontally.
Yep, 5 miles on either side. So method 2, what's our clearance?
2,005 miles.
Yep. All right. So you remember how I was telling you that sometimes Denver has to panic when they have really gusty winds? I think this might have been like the first week of class.
Yeah.
So 280, 18 gusting to 30 knots. Let's see if I can find a picture of it real quick. Wait, here we go. Okay. Okay, so when we look at these, the heading on these two runways right here, and these is all 340. Well, these are they call these 35 left and 35 right, and this is 34 left and 34 right. So if you had 48 gusting tailwind, or where was it? Let's just say that we actually had these 48 knot gusts. To give you a little hint on that, this is 26 going in right there, and then 8 going out, and then this is 25 going this way, and 7 going this way. So do you think there's going to be a lot of people landing on these if there's 48, like 30 knot crosswinds gusting to 48?
They probably closed the runway for.
Yeah, I mean, yeah, nobody's going to be landing on these. So for an airport that's used to being able to land, a lot of times they take off on 8. They'll put a lot of people taking off on 8, and they land 1 or 2 of these, and then land 1 or 2 of these. So half the time they've got like 2 to 3 runways they're landing, and like 2 to 3 runways they're taking off on. And then 7 and 5 has been having a bunch of construction and stuff on it for a long time. So they basically go down to 1 runway. They were probably operating on 1 runway today, which is why our trusty dispatcher added some hold fuel, because there was probably some holding going on as they were clearing people in. Right. Okay, now somewhere in these 72 slides, there's like 3 other important ones that I really want to go over, so I gotta find them. This is a lot of the stuff that we went over in that other one. We're also going to go over some of these charts that are on here. Okay, so these actually are kind of cool. These are the max cruise thrust. So the altitude capability tables provide maximum cruise thrust limit altitude at a given aircraft gross weight for Mach 7.4, all the speeds there. Max cruise thrust limit altitude is the altitude where a given weight with maximum cruise thrust, depending on the temperature, is selected speed can maintain in flight level. So this is basically like just with max thrust, what they can do in these planes. So this is the weight of the plane. Remember, this is the deviation from ISA. And this just thrust numbers. But basically it just means, you know, you can kind of see as it gets hotter, they get worse. Okay, this is actually a really cool one, and we'll talk about this one for a minute because you will use this in flight planning. This is a cruise table. So what this does is when we're doing flight plans by hand, what we have to do is we have to know from point to point like how far we're going, and then we have to be able to plug that into these tables. And what we're looking at here is, so this is a 250 knot table, or Mach 7.4. Oh, that's actually a climb table. So this is a climb table. So if we're climbing out and we're going, let's just say on this one, we're climbing out at 10,000 feet. I guess to 10,000 feet. This will tell us, if we look at how much distance it takes, distance, time, and then it'll actually tell us our fuel burn. So if you ever have to do stuff longhand, well, actually you guys will, at the end of this class when we do the flight planning portion, we'll use all these, but it basically tells you, you know, if you're climbing all the way up to 370 and you're weight released at 60,000 pounds, you're going to burn 1,623 pounds of fuel just to get up there. And it will take you 16 minutes to do it. Actually, I mean, yeah. So these are kind of interesting. And we'll use these much more in depth later on. Still max thrust. Let's climb, climb, climb. Okay, so this is level flight. Okay, so you remember to get up to to 28 minutes, 2,000, almost 800 pounds of fuel. These are basically just all the tables that we got, though. And then, as you can see, like, if we're super heavy, we're not making it up there to certain flight levels. These also have our ISA deviation on them up here. So this is going to be ISA plus 20. This is going to be hot. Let's go see our, it's ISA minus 10. We're actually getting a lot better performance here, but it's still not going to let us get up too high. And this is just a lot of the same stuff. So these are the descent tables. Check out the fuel burns on these. I mean, even the highest one is like up at like 400 pounds. Some of you pilots may be more familiar with this, but everyone else, when you're in the cockpit and you start descending, you'll notice they basically just pull the throttles all the way back. Like the engines are just, they're doing almost nothing. They're just kind of like spinning there. It's kind of cool. I thought the engines would still have to be doing a fair amount of work when we were descending just to keep us going forward, but they're like hardly running. And the autopilot will actually keep trying to like speed it up, and they'll a lot of times keep slowing it down to make sure they maintain their correct descent rate. These are just more descent tables for different flight levels and different weights, different ISAs. So when you're computing your flight levels later, you'll have to go in and compute your ISAs, and that's why there's so many of these tables. And this just kind of talks about a correction factor for if you have to keep your NIS on. Okay, we got to go back and talk about that. Okay, we'll have to go back up and talk about another thing, but I want to talk about this first. So our drift down. So the following minimum drift down time drift down procedure shall be used during the extended overwater operations during single engine where the maximum diversion time is limiting factor, or when minimum time to a landing is required assuming no obstacles exist. So at the first indication of an engine failure, set maximum continuous thrust on the operative engine and initiate a turn that allows for the shortest ground track to land. Descend and maintain Mach 8 till reaching 335. So continue descent at 335 knots until reaching the level off altitude provided by the level off altitude chart below. Continue at the appropriate level off altitude at maximum continuous thrust until a descent for approach and landing at a suitable airport is required. So this basically just says you have to descend below these certain altitudes once you have engine failure. And by ISA and by aircraft weight, it can change. Okay, why don't we take a quick break here? I'll come back at 8:30, and then we'll get into this next stuff. All right. Kind of what we're going to transition into talking about is takeoff and landing, a little bit of performance issues, and contaminants. So, here we go. So when we're landing and taking off, in an effort to try and standardize how everyone talks about, oh, landing was good, or landing was bad, or landing was poor, like in terms of braking action here, clearly. Sorry, that's my bad. But so for a long time, we would just kind of say, oh, braking action is good, medium, poor. There wasn't really too much we were doing. Sometimes they would take, there was a system where they would take a truck out and slam the brakes on the runway and see how far it skidded. Different things like that. But in an effort to standardize it, we actually came out with these runway CCs, so condition codes, from 1 to 5. And basically where this happened is there were starting to be a lot of accidents. One in particular was this Southwest flight in Midway. Do you guys remember this?
Nope.
You say no?
No, I've never heard of it.
Oh, okay. Well, basically what happened is there was a flight coming from Baltimore and it was headed toward Midway. And Midway actually has really short airport runways. So let me pull these up for you here. First, let me pull up and show you what St. George's are. We're all pretty familiar with how small of an airport St. George is. So St. George actually has a fairly long runway. Let's see, where is it on here? I think it's like 9,300 or something.
That's right. It's 9,300.
Is it really? Okay. Oh, it's not what I'm looking for here, but anyway, St. George is 9,300. So Midway, I'm still going to have to find it. "13 center and 31 center is only 6,500 feet long. That's this big one going down the center. So their other big one is 4 right and 22 left. And that one is 6,400 feet long. So their runways are actually really short for how, I guess, popular the airport is. There's a lot of flights that go in and out of there. So when they land there, a lot of times you'll end up with a really rough landing because they want to put it on the ground as soon as possible and then they slam on the brake. So we end up with, even sometimes we're weight restricted out of there if the runway is just wet because we have to plan very strictly. So when this all went down, Southwest, it was a flight in 2005. The airplane skidded off the runway and actually hit a car. And I believe, it'll say in this, I believe it killed a child that was in the car. while landing in a snowstorm and crashed into an automobile traffic, killing 6-year-old Joshua Woods. So, basically, everyone got together and they decided, okay, we need to do better. We need to come up with something that's a better system of how we're going to, plan these runways other than just word of mouth or, good, bad, medium, stuff like that. And it was snowing really bad during this day. These are all the day after. I actually talked to a pilot who landed just maybe 30 minutes before this plane, and he said, he was like, it was snowing real bad. He's like, we landed, and he's like, the conditions must have gotten worse since, like, even within like the 20 to 30 minutes after he landed. But yeah, even he said it. He was like, it was really bad. He's like, it was pretty slick. So we came up with these RCCs. So what we've got is 1 to 5. 5 is the best. Well, actually 0. When they're not reporting, it's the best. It's dry. It's good. Great. Wonderful. That's your normal runway. So when we have a 5, that typically means the runways are wet. So 5 is water depth of 1/8 inch or less, dry snow less than 3/4 of an inch, compacted snow with outside air temperature at or below -15 degrees. So that can be a 5. They have everything is definite, and you don't need to like memorize these or anything. Don't worry about that. But we're just going to kind of go over this and go over why. And so on landing, we have to plan to land with 60% of the runway, just because things go wrong all the time, and maybe they don't put it down soon enough, or whatever. So we have to actually plan for a pretty restrictive number. And it's a 4, somewhere between good and medium. This 3, so dry snow with 3/4 inch or greater in depth, sanded snow, sanded ice, compacted snow with an outside air temperature of -15. Why do you think this -15 matters? Does anybody know, other than heat, what can melt ice?
Salt.
Sorry, I didn't hear that. It was
Salt.
salt. Yeah, salt. Also, the big thing that we're worried about is pressure. So when we're bearing down on ice, so if you put ice between your fingers, other than just the heat from between your fingers, if you squeeze that ice, the pressure will actually help to melt it faster. So when we put this, 50, 60, 70,000 pound aircraft, or heavier, if you're not in the beautiful Canadair Regional Jet 700, there are bigger planes. Beautiful plane though, don't get me wrong. Wonderful. If you're, putting that amount of pressure on the runway, then it's going to be melting the snow below it. And when you melt it, it's going to end up a little more slick. So that's kind of why we have this -15. So at that point, it doesn't melt as much with the pressure, and so we don't end up as slick. That's kind of a weird one, not something that people typically think of. But yeah, pressure actually does melt ice to an extent, or it helps to increase the amount it's melting. So that's kind of why we have that there. 2, medium to poor, poor. Here we've got wet snow. Wet snow is pretty slick. Slush, that's real slick, you know. Water depth of more than 1/8 of an inch. So now, I mean, we could start looking at like hydroplaning. Ice that's not melting, so maybe something that's really cold. And then nil. So this is where you would get a 0, but just like the 6, we don't report it. It's just nil, we're closed. They close these runways. So this is actually like, these reports come out, in big airports, they come out all the time. But these actually prove very troublesome for us for certain airports at certain times of the day. So there are some times where we send a plane, let's say, let me pull up SkyVector and I'll show you here. So KMSP to I think this might be it. Houghton Hancock. So CMX. We do this flight during the winter, and we'll do this flight all year long. But it's way up here in is this the mitten part of Michigan? Anyway, you actually have to cross a bridge to get over to this airport, and it's like, you know, they don't staff this thing at all hours of the day like Minneapolis or O'Hare or Atlanta, you know, some of the big airports where they do have planes coming in like all the time. This thing's only open from like, it's like banker hours, like 9 to 5, and then everyone goes home. And even half the time, like they take a lunch and there's no flights, and so they just close the airport. So sometimes we take off this flight even before these people get here, or like right around the same time, and we might be looking at RCCs that they reported the day before, or something like that. Or if they get out there and they're like, yeah, it's fine, and then they change it like 10 minutes later and they're like, nope, just kidding, it's not fine, it's worse than we thought. And we've actually had planes go up here and different RCCs reported and they could not land and they diverted. Just hopefully the dispatcher planned. That's kind of one of those things that you know by word of mouth and people give you a heads up about. So hopefully the dispatcher kind of looked at the weather from the night before and thought, okay, well, maybe the runways weren't as good as we thought, and they planned an alternate. If not, they might have just been chucking down here to, I think Green Bay's like right here. Somewhere down here. There it is. Might go down here or down to Escanaba, but yeah. So it's kind of a rough deal. Sometimes they just they change them on you, and there are other times where it'll be like wet snow or slush, and then all of a sudden the temperature drops real quick, and we just end up with ice. So these are kind of just interesting to think about, and they kind of give you a little definition. So braking deceleration is normal for wheel braking effort applied. Directional control is normal. Sometimes you'll actually get 3s, and it's slippery when wet. And what that is like it's rubber on the runway from all the tires landing. And then if it rains and it gets wet, that all the oils come up and the rubber gets really slick. So that one comes up as a 3 instead of a 5, which is normally just wet. And that one actually proves really troublesome for us because we can't land on 3s if we have a thrust reverser out. Okay, so that's landing. Clearly landing, we've got to be able to, put the plane on the ground and bring it to a safe stop. You don't want to end up skidding off the end of the runway. What about takeoff? How do you think this affects takeoff for us?
I think it's probably even more dangerous.
Yeah, it probably actually could be. The big thing for takeoff for us is that if we're slam the engines to the floor and we're like chucking along and then we have an engine failure, if you're soon enough in your engine rollout, you hit the brakes and you try and come to a stop before the end of the runway. If you are literally like rotating up and you're like way down the runway and you might be like rotating up, but your back wheels are still on the ground or something like that, and you have engine failure, you still have to take off, and then you got to come back around and you got to be able to land on it. So with one engine out, do you think you really want to come back around and land on ice? Even though we might be able to take off, we might be able to make it down the runway on a 1 with ice, but we've always got to think about what if an engine fails. We basically just have to go ahead and plan our entire flight around what if an engine fails? What if we only have 1 engine? So yeah, nobody wants to come back around with 1 engine because then you've only got 1 thrust reverser and you're trying to stop a plane. So the big thing for us there is when we take off, can we get to a safe speed to take off the plane and then have to come back around if we have engine failure? Or if we're going along and we have engine failure, can we stop the plane? So that's really big for us. And our big thing with takeoff too is takeoff. A lot of it is about our performance comes from our weight and balance, which we talked a lot about on Friday. So these are all kind of different things. I was supposed to find some spaghetti charts for us to look at for takeoff, but I have not been able to find them. So I guess that was about all we were going to go over today. Unless there's something I didn't remember down here. Oh, This just kind of gives you a visual, like with ETOPS, like where you're allowed to fly. So we're not doing ETOPS, so we can still fly out over water. We just have to make sure we're close enough to land. Does anybody have any questions? Well, I reckon that we're going to finish up here about 30 minutes early. I'll have to talk to Garrett and see if he can find the spaghetti charts that we were looking for takeoff. But let me see. Let me take my screen off and see if I can find this week's quiz. Can you guys still see my screen? Nope. Okay. Maybe we can do a bit of a review, and that'll keep us from ending a full-blown 30 minutes early. And okay, so what are we always planning for when we're planning for these flights?
Engine failure.
Yeah, one engine inoperative. So method 1, what's our clearance?
1,000 feet, 5 miles on either side.
All right, nice. What about drift down 2? Method 2.
If you have an obstacle in the way, then turn around to your alternate.
And what's our clearance?
It's 2,005 miles.
Yep. What kind of things does ATC do to help manage traffic? So what are a couple of things they do?
They time the landings.
Yeah, so we're looking at one of the first things they can do is they can issue a ground stop. So that stops all aircraft that are heading to, so if Salt Lake issues a ground stop, all aircraft that have the destination of Salt Lake City are held on the ground. They're not allowed to take off. Or we can do a ground delay program, which they basically assign you a time to take off, and that helps to manage the flow and helps to slow down the flow. They can also do, you remember we talked about miles and trail? So they're looking at, like the time in between the planes. And they can kind of zigzag you around to slow you down, or they can slow you down your speed to create more space. Holding is typically their last resort. They don't want to hold people. Okay, what does NOTAM mean?
Notice to airmen.
Notice to airmen. A lot of it is the takeoff performance. And then a couple things with MELs. All right, do you guys have any questions?
When are we taking the quiz?
That is a good question. I actually don't know. I was talking to Garrett earlier today, and I totally forgot to ask. So
not tomorrow.
no, I wouldn't think that it's tomorrow. I think he would have told me to go over more stuff if it was tomorrow. So should be good on there. Well, all right.
What about the last quiz? I haven't seen the graded last quiz. Am I just missing something?
No, I don't think it's been graded yet. So I think we're still waiting on those. But all right. I guess we'll end early tonight. Unless anybody else has any questions.
Nope, got a half hour to study for the ADX.
Yeah, there you go. Use this half hour to study.
Exactly.
Perfect. Yeah, you're welcome then.
Thank you very much.
I'll tell Garrett though. He may want to run across those spaghetti charts tomorrow. We'll see. But alrighty. Y'all have a good night.
Thanks,
Thank
Davis.
you.
You too.